Now let's continue with the second part of the same problem. For these given matrices M and M, part B says express the matrix products of part A using the subscript summation notation, and then part C, convert the following expressions which are written in subscript summation notation to matrix notation. So let's see what we did here when we multiplied matrix M with matrix N. This can be written in subscript summation notation. So I look at the ith row jth column element of the matrix M and add to it, multiply it with the jth row kth column element, and the summation is over the index j. So this is my subscript summation notation. So if I look at, let's see here, n times M, matrix N multiplied with matrix M, I have a similar situation. This written in subscript summation notation. I'm taking the ith row jth column element of the N matrix, multiplying it with the jth row kth column element, and add over the index j. So let's just check this here. So to calculate n times m, for example, if I is equal to 1, j is equal to 1, multiplied with j is equal to 1, k is equal to 1, then I have I is equal to 1, j is equal to 2, multiplied with j is equal to 2, j is equal to 2, k is equal to 1. So you can see here, I'm adding over the index j. So the column number of the first matrix and the row number of the second matrix is what we are adding over here. And finally, if I want to write the M matrix multiplied with M matrix, this has a representation in subscript summation notation, very similar to the previous cases. Mij, M, Jk. So ith row kth column element of the product matrix is given by Mij, Mjk, where we have a summation over the index j. So that's what we have done here. So for example, if I'm looking at the second row first column element, that is I is equal to 2, k is equal to 1. Okay, so for this one, I have to do I is equal to 2 multiplied I is equal to 2, j is equal to 1 multiplied with, for this element, j is equal to 1, k is equal to 1, plus then I have I is equal to 2, j is equal to 2 multiplied with j is equal to I is equal to j is equal to 2 and k is equal to 1. So that basically matches what I have done here. I just checked it for this element. Okay, so let's move on to part C. Now we're going to convert these expressions to matrix notation. So what is the meaning of mjk and ij? Let's start with that. The first one, M, J, K, N, I, J. You see we have a common index here, the J index. So if I write this, this is just the product of two numbers. I can change the order, Nij, Mjk. So I'm just changing their order in the product. And the summation is over J. This is going to give me the ith row, kth column element of the product matrix. So what I'm really doing here is, in matrix notation, multiplying the N matrix with the M matrix. So that's the meaning of this in subscript summation notation. So that's the first question, MJKNIJ, which is what I did here. And the second one is MIJ and KJ. So let's work on that. MIJ and KJ. Now you can see, in order to perform the multiplication, I should have Mij and Jk, but this is K and J switched places here, so the rows and columns have switched places. So what this is actually the matrix M multiplied with the transpose, because it has switched rows and columns, of matrix N. So the N matrix is represented in subscript summation notation as NJK, and therefore N transpose matrix is represented in subscript summation notation as NKJ. Okay, let's move on to the third one. The third one is MJI and JK. MJI and JK. Now you can see that representing my M matrix here using the subscript summation notation with Mij. So Mij and Jk would be giving me the product of M matrix with N matrix. So the transpose of M matrix, which has the positions of the rows and columns switched, would be Mji. Therefore, what I have here is the transpose of the M matrix multiplied with the N matrix and JK. Okay, let's move on to the fourth one. Mij and JK plus TKI. Mij and JK plus TKI. So the repeated index, J index, implies summation in subscript summation notation. So summation over J, because J is the contracted index. So Mij times Njk is basically the product of the M matrix with N matrix. So let's call this new matrix L matrix. Okay, so with that, you can see Mij and Jk implies we're looking at the contracted index is J, L, I, K, ith element of the L matrix. Now, if the T matrix has an ith element, ith row, kth column element, so this is represented with Tik, then we see that Tki would correspond to transpose of this matrix. So looking at the relationship between the two indices here, Lik plus Tik would be giving me L matrix plus T matrix, but this is Tki, then it is the transpose. So this tells me that I have Lik plus Tki, which is, in matrix notation, the product of M matrix, multiplication of M matrix with the N matrix, and plus I have the transpose of the T matrix. So that's the answer for this one. And the last one, the fifth one, is Mji Nkj plus Tik. So let's look at that one. Mji Nkj plus Tik. Now rearranging this is actually Nkj Mji plus Tik. I can change the order of the product here, and I see immediately that J is a contracted index. It implies summation. So if M index is represented in subscript summation notation with Mji, and N index, N matrix is represented with Nkj, then Nkj times Mji implies we have the product of the two matrices, N matrix multiplied with the M matrix. All right. And this gives me the L matrix, where J is the contracted index. So in the subscript summation notation, I have Nkj Mji, and that means the indices of the L matrix are Lki because the J is contracted. Now I have Lki plus Tik. So if Tik is the T matrix, then Lki is the L matrix with the switched positions of columns and rows. So I can interpret this Lki plus Tik as the transpose of the L matrix plus the T matrix. That's one way to see it. And therefore, I see that N matrix multiplied with the M matrix gives me the L matrix. So if I take the transpose of this actually gives me M transpose multiplied with N transpose. When I take the transpose, the positions also change, so that this LKI plus TIK should be interpreted as LKI is multiplication of M transpose with N transpose plus the T matrix. So that's how we can see the matrix notation. Okay, so in this part of the problem, first we checked our matrix products. M and matrix products means we have Mij and Jk. The ith row kth column element of the product is given by Mij and Jk element products summed over the index J. Similarly, n times m is Nij mjk, m times m is Mij mjk. So ith row kth column element of the product matrix is given by the first matrix ith row jth column multiplied with the second matrix jth row kth column and is summed over J. Now, what is the meaning of mjk nij? That's equal to nij times mjk. The two numbers can be switched in the multiplication. J is the contracted index. This gives us the ith row kth column element of the matrix, the product matrix, n times m. Now, what is the meaning of Mij and Kj? So if n matrix is njk and transpose is nkj, so Mij and kj, the j is in the wrong position for this product. So this tells me that I'm taking the transpose of the second matrix. So it should be nkj. That's the transpose. So this is M matrix multiplied with N transpose. Now what is Mji and Jk? Now J is in the first position. If M matrix is Mij, transpose is Mji. So the transpose of the matrix M multiplied with matrix N. Mij and Jk, that's M and matrices product, which gives us the ith row kth column element of the product matrix plus tki. Since ik and ki are in the wrong positions here, this should be T matrix transpose. So I and K have switched places. So that means I have M times N plus T transpose. And finally, Mji and Kj or nkj mji, that's N matrix times M matrix, gives me the kth row ith column element of the L matrix, but I'm adding to it the ith row kth column element of another matrix. So L matrix should have been transposed. So if N times M is L, then M transpose times N transpose is L transpose. That's how I interpret this one. Plus the T matrix is what I'm looking for.